A clay jar could change how we think about ancient technology. That jar is called the Baghdad Battery. It's been argued about for decades. The question is whether an ancient society discovered electricity long before we believe they could have. Or if it's just a story we like to tell. I want to show you what modern testing reveals about it. We've done experiments, building copies of the jar to see how much power it can actually produce. To see what it was capable of, one theory is that it was used for electroplating, for putting a layer of gold onto other metals. Another is that it was just a sealed vessel for holding important documents. After seeing the tests, you can look at the evidence yourself to figure out what's real ancient invention and what we might be imagining. It makes you wonder about what innovation really is and how it appears over time. They found it in the dry ground near Baghdad back in 1936, something that didn't belong, a small clay jar sealed with asphalt, inside a copper sheet rolled into a cylinder. And inside that, an iron rod, common materials really, but put together like that, it looked intentional, almost engineered. They dated it to the Parthian or Sasanian period, somewhere between 250 years before the Common Era and 250 after. A time known for empires, for art, not for experiments, so it got catalogued, set aside, a curiosity, until Wilhelm König saw it. He was a German archaeologist working there. And he looked at this jar, the copper, the iron, the asphalt, and he thought, what if it wasn't for storage? What if it was a battery, a simple idea? Fill the jar with something acidic, vinegar maybe. The electrolyte touches the two different metals. Copper becomes one terminal, iron the other. You'd get a small voltage between them. It made a kind of sense. But the reaction was immediate, deep skepticism. Critics said it was seeing what you want to see. Each part had more plausible uses. Asphalt was a sealant for keeping scrolls safe. The copper cylinder could have held a document. The iron rod might have been a core. The idea that ancient artisans stumbled onto electricity, it felt like a fantasy. A modern idea projected onto the past, so the burden of proof was huge. Koenig's hypothesis needed more than a guess. It needed the object itself to show something undeniable. That tension between a radical idea and the established story, that's where it all begins. It makes you ask, what can the thing actually do? The jar is a simple thing. About 13 centimeters tall, it's made from a buff-colored clay, common in that area, but the inside is different. There's a copper sheet rolled up. About 10 centimeters long, forming a cylinder just over 2.5 centimeters wide. This copper tube isn't soldered shut. It's held together with a lead tin alloy. That's a detail. It shows thoughtful metalwork, and suspended right down the center of this copper cylinder is an iron rod. The rod is a little shorter. And it doesn't touch the copper walls. It's held perfectly in place by a thick plug of asphalt, sealing the jar's mouth. That asphalt is a major clue. It's an excellent electrical insulator. If this was just a storage jar for a scroll or some sacred oil, a simple cork or clay lid would have worked. The choice of asphalt, which you'd have to melt and pour, suggests a need to isolate the central rod from the outer cylinder to keep them from making contact. And on that iron rod, researchers saw something. It showed signs of acidic corrosion, not the kind of rust you get from age and moisture. It was the specific pitting that happens when iron is exposed to an acidic electrolyte, like vinegar, and then subjected to a small electrical current. Now, the mainstream interpretation. Many archaeologists see a practical storage vessel. The copper cylinder could have held a precious scroll. The iron rod might have been a stiffening core for that scroll. Or a ritual object. The asphalt seal would just be a way to keep everything dry and secure. It's a logical, utilitarian explanation. There's no need to invoke electricity. But when you visualize the two setups side by side, the difference is striking. In the storage scenario, the components are passive, just things held together. In the battery scenario, they become an active system. The jar is a container for an electrolyte. The copper and iron are two different electrodes. The asphalt is an insulating gasket. The corrosion on the iron isn't damage, it's evidence of function. This is why the object's anatomy is so debated. Every single part can be read two ways. To move past this, we have to stop just looking at the artifact. We have to start asking it to perform. We have to build a copy, fill it, and see what happens. The idea needed something to make it real. That came from an American engineer, Willard. In the 1940s, he read about König's battery idea. And he didn't just talk about it, he tested it. He built a copy. He used the published dimensions of the Baghdad jar. He made his own version with a terracotta pot, a copper cylinder, and an iron rod. He sealed the top with asphalt. For the electrolyte, he used grape juice. It's acidic, it was available. He poured it in, connected a voltmeter, and the needle moved. It showed a small voltage, about 1.5 to 2 volts. That's like a single AA battery. To show it could work, Gray connected several replicas together. The combined voltage gave a faint tingle on the tongue, or it made a very dim glow in a small glass vial, a gold leaf electroscope. It was proof of concept. The chemistry worked. The clay, the copper, the iron, and an acid could make electricity. The reaction to his experiment was mixed. For supporters, it was a eureka moment. The object functioned. It wasn't just a jar, it was a power source, but for skeptics, it raised more questions. Yes, it made a tiny current, but to what end? What use was that power? A faint tingle, a dim glow in a lab. That wasn't an application. It felt like a parlor trick. Gray's work was vital, but it set a frustrating baseline. He proved the jar could be a battery. He did not prove it was used as one. The gap between possibility and purpose was still wide open, a challenge for the next people to confront. Gray's grape juice idea got things started, but it also kind of boxed the question in. To figure out what the jar really was, you have to picture an ancient workshop. You have to look at the shelves. What liquids did they actually keep around? That's the electrolyte puzzle. The power isn't just in the metals. It's in the reaction between those metals and whatever acidic thing is inside the jar. And what you choose to put in changes everything. Vinegar is the obvious one. It was a common household thing for preserving food, for cleaning. Its acetic acid gives you a steady, mild electrolyte. Then there's fermented fruit juices, pomegranate wine gone sour, date wine turned. Those were around too. Their organic acids are a little more complex, but they'd work. And then there's a more interesting idea, the clay itself. Some local clays, when you mix them with water, create a slightly acidic environment from their minerals. So the jar wouldn't even need a separate liquid poured in. The material it's made from could be part of the reaction. Each of these has a different character. Vinegar gives a steady, predictable voltage. Fruit juices can vary, sometimes a stronger initial jolt that fades as the sugars break down. A clay slurry might give a very weak current, but one that lasts a long time as the minerals slowly dissolve. In modern tests, a single replica jar gives you about half a volt with a weak electrolyte, up to nearly 2 volts with something strong and fresh, like lemon juice. The current, the actual flow, is tiny with any of them, just a few milliamps, enough to feel on your tongue, or to very slowly move metal ions in a solution. Not enough to light a bulb in any real way, so you have to wonder, if an ancient artisan was experimenting, which bottle do they reach for? The one that gives the biggest spark, or the one that's most convenient, most stable? Vinegar wins on practicality. It was everywhere, it was consistent, it wouldn't spoil quickly in a sealed jar. A discovery doesn't have to start with the perfect lab chemical. It often starts with whatever's sitting right in front of you, solving this practical puzzle, what to pour into the jar, that moves you from a theoretical possibility to a grounded historical scene. It turns a mysterious object into a potential tool, something waiting on a bench next to a vat of vinegar and a spool of gold wire. The debate left the workshops and went into the lab. To really settle this, a working replica isn't enough. You have to ask the original artifact itself what happened to it over the centuries. That's where modern materials science comes in. They used tools like electron microscopes, X-ray fluorescence, to look at the Baghdad Battery in a way its makers never could. They examined the corrosion on that iron rod with forensic precision. That pattern of pitting and decay is a historical record. If the rod was part of an electrochemical cell, the corrosion should show a specific signature, galvanic corrosion, from a sustained, low-level current in an acidic environment. And the analysis suggests it does. The corrosion isn't uniform, not just rust from damp soil. It shows that localized, aggressive pitting you'd see on an anode in a primitive battery, where the metal dissolves sacrificially to produce electrons. That finding is a significant data point. It moves the needle from coincidence toward intention. Then there's the metallurgy. The copper cylinder isn't pure. It has traces of other elements like ancient smelted copper often does. But was it chosen or refined for a particular property? The iron rod shows its origins too. Neither metal appears to be a special, purpose-made alloy. They're typical materials of the period for everyday objects. That fact cuts both ways. For skeptics, it means no advanced metallurgical knowledge was applied. For proponents, it makes the idea more plausible. A discovery doesn't require special materials. It often comes from tinkering with what's already on hand. An artisan noticing a strange tingle when a vinegar-soaked cloth bridged an iron tool and a copper pot. That could have been the spark. The scientific analysis doesn't deliver a verdict. It provides a new, more detailed map of the evidence. We now know the corrosion supports the battery model. We know the metals were ordinary. This forensic layer strips away some speculation and replaces it with hard data. With that map in hand, the next step becomes clear. You can design a new generation of replication experiments, not based on guesswork, but guided by the material truths the artifact itself has revealed. They wanted to build a historical twin, not just a working model. A team of researchers stepped away from modern tools. Their goal was to reconstruct the Baghdad Battery using only what a Parthian or Sasanian artisan would have had. This wasn't about proving a chemical principle anymore. It was about walking into an ancient workshop, seeing if the design made sense there. They started with the clay. They gathered local earth, tempered it with sand, hand-formed the jar on a simple wheel, fired it in a wood-burning kiln. The process was slow, imperfect. The vessel was porous, and that was a problem. A battery jar can't leak. The electrolyte has to stay contained to maintain contact with the electrodes. So they experimented with sealing the interior. They tried beeswax. It was too soft. They settled on a thin layer of natural asphalt, heated until liquid brushed inside. A tedious, smoky process, but it worked. The jar became a non-conductive, waterproof container. Next came the metals. Instead of buying copper sheet, they smelted copper from malachite ore. In a charcoal furnace, the resulting ingot was hammered into a thin, rolled cylinder. The seam sealed with a lead tin solder they sourced locally. The iron rod was forged from bog iron. Accessible in that period, it wasn't perfectly straight, not perfectly pure. It was exactly the kind of rough, functional rod an ancient metalsmith would produce. For the electrolyte, they chose date vinegar. Dates were a staple. Their fermentation into vinegar was a common preservation method, a liquid you'd find in any household. They filled the sealed jar, inserted the iron rod through the asphalt plug, and waited. They connected their handmade copper and iron terminals to a modern voltmeter. The only concession to the present day, the needle climbed, settled around 0.8 volts. The current was minuscule, measured in microamps, less than Willard Gray's grape juice version. But it was steady. Over days, the voltage remained consistent, a quiet, persistent hum of energy. This was the output of a truly ancient process. So what could this tiny trickle of power actually do? It couldn't light a lamp, couldn't power any device we recognize, but it could, over many hours or days, cause a transformation in a solution. If you placed two metal objects in a bath of gold salts, a solution containing dissolved gold, and connected this weak battery between them, the gold ions would slowly migrate, atom by atom, from one object and plate onto the other. This is electroplating, a subtle process, invisible to the eye as it happens, but yielding a solid, gleaming result. A low, steady voltage is actually ideal for this. A high voltage would cause a rough, uneven coating. This slow deposition produces a smooth, adherent layer of gold. The experiment did more than generate a fraction of a volt. It demonstrated that the artifact's specific design, its sealed jar, its insulated central rod, its choice of common metals was perfectly optimized to produce exactly the kind of gentle, sustained current needed for one very specific, very valuable ancient craft. The object in the museum case suddenly looked less like a storage jar and more like the core component of a delicate, sophisticated workshop tool. That steady half-volt is the mystery. It's the core of it. To make sense of it, you have to translate it. Think of voltage as pressure, like water in a hose. It's the push. The replicas create a gentle push between half a volt and 1.5. A modern A battery is about 1.5 volts. So it's a similar range. The big difference is the current. That's the flow, the actual water moving through. The ancient cell gives you a trickle, a few thousandths of an amp. A battery can give you a torrent, enough to spin something, to light something bright. So this thing had the pressure but not the flow. You felt a tiny power like that. That snap from a doorknob after walking on carpet, that static shock can be thousands of volts, but it's a single burst, almost no current. The Baghdad Battery is the opposite. A low, constant pressure with a tiny, continuous trickle. It's not a spark, it's a whisper. Now, one whisper isn't much, but whispers can be combined. If you link several cells, copper of one to iron of the next, you add their voltages together. 10 jars could give you 5 to 10 volts, a slightly stronger trickle. And here the record goes quiet. No one has found a set wired together, no ancient terminals, no connecting wires found in a way that suggests a battery bank. That absence is a point for skeptics. If this was a technology, wouldn't we see it scaled up? But the simplicity is compelling. An artisan wouldn't need theory. They'd just need to notice. Touching copper from one jar to the iron of another gives a stronger tingle on the tongue. Experimentation through sensation could lead to a series connection. But the wires would have been perishable, metal strips, moistened threads, they'd vanish. So we have this gap. The design allows for scaling up, but no proof it was ever done. Which leads to the practical question, what can you do with half a volt and a trickle? You can't light a lamp, not even a faint one. You can't power a motor. Any real tool, it feels useless, a curiosity, but that's a modern view, looking for flashes, for movement. If you shift to the slow world, the invisible world of chemistry, then this kind of gentle, sustained power becomes potent. It's the perfect tool for a specific ancient craft, one that transforms a surface, makes something ordinary into something luminous. Precious, so the search turns from electrical output to chemical reaction. Gold has always gleamed in the dark. Ancient artisans wanted that prestige for common metals. They used fire gilding. You'd paint on a mix of gold and mercury, then heat it. The mercury burns away, leaving gold behind. It worked, but it was dangerous. The fumes were poisonous, the coating could be uneven, it took a lot of skill to do it safely, and it wasted gold. Then there's the battery idea, electroplating. A gentle method. You have a liquid with dissolved gold in it. You put two objects in the bath. One is the item you want to plate, connected to the battery's negative side. The other is a piece of gold connected to the positive side. You close the circuit. A small, steady current flows. Positively charged gold ions move through the liquid. They deposit onto the negative object, atom by atom. Over hours, a thin, even layer forms. It sticks tightly. It can cover fine details without filling them in. No dangerous fumes, and it uses very little gold. Now, look at the artifacts from the Parthian and Sasanian periods. Objects with very fine, uniform gold coatings. A silver statuette with a thin gold robe. A copper pendant with a flawless gold sheen. The work is exquisite. Could fire gilding alone do that? Maybe, with incredible skill. But electroplating explains the precision. It's about control, not force. The battery's output is actually perfect for this. Low voltage, minimal current. High power would make a rough, brittle coating. This slow trickle gives a smooth finish. An artisan could set up a vat, connect a few battery jars for more push, and plate items overnight. The result is a coating so uniform it seems impossible. The materials were available. A gold salt solution could be made from natural minerals, or by dissolving gold in acids from vinegar and salt. All within reach, but skeptics have a point. Where are the wires? Where are the electrodes? If this was a practice technology, we should find the toolkit. Copper clamps, iron hooks, special vessels for the plating bath. We don't. They say the fine gilding could be from advanced chemical processes or from meticulous gold leaf application. And there's no written record, no depiction of an electrical process. If it was used, why is it never mentioned? This application is the heart of the mystery. It turns the battery from a curiosity into a potential workshop tool. It links voltage to a tangible outcome, beauty and prestige. Whether it was actually used this way is still an open question. But it gives a compelling reason for such a device to exist, to be developed, cherished, and then perhaps forgotten. Its true purpose sealed away like the asphalt plug on that clay jar. A tingling sensation on the skin, that feels like magic, and that's the second path the battery could have taken, not toward craft but toward the body. Toward the spirit. Ancient cultures understood natural forces long before they had a theory for them. Greek and Roman medical texts show that. Physicians prescribed the touch of an electric fish for certain ailments. A torpedo ray. Patients with gout or headaches would stand on a wet shore. The living fish was placed against their skin. The numbing jolt that followed was thought to soothe pain. This wasn't superstition, it was an observed effect, a therapeutic effect harnessed without understanding the mechanism. It proves a concept was there in the ancient world. The concept that a mysterious, invisible force from certain objects could interact with the human body. Now put a Baghdad Battery replica into that context. Its output is a faint, continuous tingle. That's remarkably similar to the low-level stimulation used in some modern pain devices. A priest or healer, someone knowledgeable in herbs and rituals, might have discovered this by accident. While preparing the jar with vinegar, their wet fingers bridged the copper and the iron. A strange, persistent buzz traveled up their arm. In a world where illness was often a spiritual imbalance, such a tangible, mysterious force would be incredibly powerful. It wasn't just a tool, it was a conduit for divine energy. Imagine a ritual chamber, a patient in discomfort. The healer prepares a special mixture, pours it into the sacred vessel. They speak incantations. Maybe they attach a thin metal foil or a moistened cloth to the jar's terminals. They apply it to the patient's temple or limb. The sensation is undeniable. A gentle, humming vibration where there was only pain before. the effect, whether placebo or genuinely therapeutic, would be profound. The battery becomes a ritual object. Its power validates the healer's authority. It validates the community's beliefs. Its design adds to that, sealed with mysterious asphalt containing hidden metals. That only adds to its sacred aura. Yet here, the historical silence becomes deafening. For all the detailed records from Mesopotamia, the meticulous lists of temple objects and medical recipes and ritual procedures, there is not a single clear description of such a device. No depiction on a relief shows a priest holding wires from a clay pot to a person's head. This absence is the strongest argument against this application. If it was a widespread medical or ritual technology, why would it leave no trace in a culture that recorded so much? This speculation opens a window nonetheless. A fascinating window. It asks us to consider how a technological discovery might be absorbed, not into industry, but into the realm of belief. The same object that could plate gold onto a statue could also be seen as a vessel for a healing spirit. Its true function might have been less important than the experience it created. A forgotten tool, its purpose faded, leaving behind only a curious jar. A mystery that buzzes with possibility, waiting for a connection to be made. You look at that jar and you can see a battery, but there's another way to see it. A simpler way. Archaeologists look at the same object and see something ordinary. They point to other finds from the region, clay vessels sealed with asphalt or wax. And inside, you find what you'd expect: papyrus scrolls, parchment. This was a common method, a way to protect documents from moisture, from insects in a dry climate. The Baghdad jar fits right into that tradition. The copper cylinder wasn't an electrode. It was a protective case for a scroll, maybe a religious text, a legal document. The iron rod wasn't an anode. It was a core, a stiff rod you'd roll the parchment around to give it structure, to keep it from crumbling. The asphalt plug wasn't an insulator. It was just a seal, a waterproof sealant readily available, used to preserve the contents. This view doesn't need unknown technology. It uses practices we already know existed. It's practical. Then there's the corrosion on the iron rod, the pitting. Battery theorists say that's from an acidic electrolyte. But if the jar held an organic scroll over centuries, that scroll would decay. Decomposition creates weak acids. Trapped inside a sealed jar, those acids could slowly eat away at the iron. So the corrosion is natural. It's from storage, not from use. The artifact wasn't operated. It was just stored, and time did the rest. This skeptical view leans on a principle, Occam's razor, the idea that the simplest explanation is usually the right one. And here, the assumptions are very different. The battery story assumes an ancient discovery of electrochemistry, a practical use for its power, and then a complete disappearance of that knowledge from history. The scroll story assumes people used common materials in common ways to solve a common problem, preserving writing. One path is filled with mystery, with lost genius. The other is straightforward ancient ingenuity, and the absence of evidence matters. If this was a working electrical device, even a rare one, where is everything else? Where are the wires, the connectors, the terminals? We've found countless tools from these eras: looms, kilns, surgical tools, writing styli. Not a single object has been identified as a clear component for using a battery. No depictions in art, no mention in the meticulous written records. For a technology, that silence is deafening. It suggests that if electricity was known, it was a curiosity. Never developed, or more likely, it was never electricity at all. This isn't about dismissing wonder. It's about rigorous investigation. It reminds us that our desire for lost advanced knowledge can color what we see. The real mystery might not be how they made a battery. It might be why we're so captivated by the idea that they did. It challenges us to separate the romance of the past from the artifacts it actually left behind. And that makes the question more compelling, Because if it's not a battery, then what was inside? What was so valuable it warranted this careful, deliberate construction? The mystery just shifts from a spark of technology to a whisper on a vanished scroll. They tested the storage idea. They built a replica of the jar, the copper cylinder, the iron rod. They used papyrus, wrote on it with iron gall ink, rolled it around the rod, put it in the cylinder, sealed it with asphalt. They made a control jar empty. Buried them both in soil that matched the conditions near Baghdad. They cycled the temperature and humidity to speed up time. They waited months. The question was whether the corrosion would match. When they dug them up, the papyrus had degraded, but the rust on the iron rod was different. It was a general, uniform rust from dampness from the weak acids of decaying organics. It didn't have that specific galvanic pitting, the pitting the battery theory predicts. And then there was the design itself. A copper cylinder was an incredibly expensive scroll case for that period. Most scrolls used clay tubes or leather and an iron rod for a core. Usually they used wooden rods. Wood was lighter, cheaper, less corrosive. What they built worked. It stored the scroll, but it was like using a titanium case for a sheet of paper, functional but over-engineered. This didn't disprove the storage idea. But it showed the corrosion might not match, and it raised the question of why a scribe would choose this complex, metal-heavy design when simpler methods were everywhere. That's how the inquiry moves. You test every plausible idea with the same rigor. The outcome isn't always an answer. Sometimes it's just a clearer set of questions. That clay jar wasn't isolated. It came out of a time of real innovation. The Parthian and Sasanian periods, they weren't dark ages. They were times of high technical skill. Their engineers mastered the kanat, these underground canals that moved water across dry landscapes using just gravity. They built complex gear systems too, like the Antikythera mechanism from the Hellenistic world, which shows a deep understanding of mechanics and astronomy. Their artisans were expert chemists. They worked with acids and alkalis long before those were formal terms. They used ferric acetate made from vinegar and iron as a mordant to bind dyes to fabric. They used strong acids from salt or vitriol for etching metal and refining ores. They knew that combining certain substances could create dramatic changes. A color shift, a metal dissolving, a new compound forming. This was a practical chemistry, an art of effects, not abstract theory. So an artisan mixing vinegar, copper, and iron and noticing a strange, persistent tingling that fits right into their world. They wouldn't call it a voltaic cell. They might call it a curious property of certain materials, a workshop secret. The gap in our understanding isn't whether they could have stumbled on the effect. It's whether they recognized it as a distinct, useful phenomenon worth developing. Could a single workshop have discovered electroplating as a better alternative to fire gilding, perfected it in secret, and then had that knowledge vanish completely? It's possible. Guilds guarded their techniques fiercely. A master jeweler's method for applying flawless gold could be his most prized secret, passed only to an apprentice. Its loss in a war or social upheaval would be total. But technology usually leaves a wider footprint. It spawns variations, imitations, it evolves. The complete silence around this one device, amid so many other recorded innovations, is what makes historians pause. It asks us to consider how knowledge lives and dies. Is it a continuous chain, link by link, or can it be a single, bright spark in one place at one time that just winks out? The context suggests the spark was possible. The silence suggests it may never have caught fire. That tension brings us to the final, most direct way to seek an answer. To stop debating the past and instead, quite literally, put the idea to the test. An iron chisel left in a copper bowl of vinegar overnight. The next morning, someone reaches in and feels a faint buzzing on their wet skin. They pull their hand back. Over days, they see the iron has changed, not just rusted but etched in a pattern. In a world without electricity, how do you explain that? It might seem like a spirit in the metals awakened by the sour liquid. So you ritualize it, you repeat the process with ceremony to control that force. The Baghdad Battery could have come from that, not from a theory, but from trying to recreate an intriguing effect. The asphalt seal keeps the liquid in. The iron rod is centered, not touching the copper, to maximize the tingle. Each iteration improves the design based on feeling alone. That's innovation through serendipity, guided by tinkering. The opposite view is intentional design from the start. An ancient thinker wants to plate gold without fire. They experiment systematically. They reason a sealed container prevents evaporation. They choose copper and iron for their different properties. They plan the assembly as a tool for a specific task. That's a different kind of genius, one of foresight and engineering. Both paths are possible, and they show how technology blossoms. It's rarely a straight line from theory to invention. More often, it's a dance between chance observation and purposeful refinement. Someone notices something odd. They play with it, shape it, and eventually give it a use. The Baghdad Battery embodies that dance. It asks us to see ancient innovators not as primitive or as secret scientists, but as attentive craftspeople. People familiar with their materials, always watching for the unexpected whisper of a new possibility. Whether the jar is a battery or a scroll case, its existence speaks to that capacity for wonder and iteration. The mystery isn't just about volts and electrolytes. It's about the moment a spark of curiosity was captured, in clay and copper and sealed with asphalt, waiting centuries for us to understand its original flame. The search for ancient electricity, it doesn't end in Baghdad. You hear about similar objects from other times and places. Each one could be a piece of a puzzle. In Egypt, for instance, there's the dendrolite. It's a carving on a temple wall, shows a large bulb-like shape with a snake inside held up by a priest. Some people look at that and think it's an ancient electric lamp, but Egyptologists have an explanation. They say it's a sacred ritual, a symbolic scene. Probably shows the creation of a sun god from a lotus flower. The snake represents divine power, not a filament, and the carving fits. It fits right into known Egyptian religious art. There's no text, no other artifacts that suggest electrical use. It's a spiritual symbol, not a technical diagram. Then from the Americas, there are stories. Artifacts found in Central America, sometimes called primitive batteries or electrical devices, but these claims are often vague. They lack clear documentation. They haven't gone through peer-reviewed analysis. Usually the objects could be something else, ceremonial items or tools or just natural formations. Without something like the Baghdad jar, a well-preserved object with that distinct separation of two different metals inside an electrolyte container, these stories stay in the realm of speculation. They show a pattern, really. Our modern fascination with electricity can make us see it where it probably never was. This global view shows something. Shows something about us, the desire to find lost high technology in the ancient world. It's a powerful story. It speaks to a sense of wonder, maybe a hope that past civilizations had secrets we've yet to rediscover. But that desire needs to be tempered by a respect for the cultures themselves. If you force a modern, technological interpretation onto an object, you can strip away its real cultural meaning. A ceremonial vessel becomes a battery cell. A religious symbol becomes a blueprint. You risk losing the actual story, the beliefs, the artistry, the daily life, while chasing a more thrilling tale that isn't as well supported. And this is why the Baghdad artifact is different. It's not a carving open to symbolic interpretation. It's a physical object, three-dimensional, with a specific, engineered construction. The copper, the iron, the asphalt insulator, these are tangible parts. You can test them. Its purpose is debated, but its form is clear. It's the only artifact of its kind that aligns so neatly with the principles of a galvanic cell. That makes it the central piece of evidence in this whole discussion that's gone on for centuries. Its uniqueness doesn't prove it was a battery, but it does demand a serious scientific inquiry. The kind other, more speculative claims don't merit. It places a responsibility on us to interpret it with open-minded curiosity, but also with disciplined scrutiny. To honor the mystery without inventing answers it can't give, the artifact didn't stay in the lab. It left the museum case and went into our imagination. By the 1970s, the Baghdad Battery was a star. It showed up in popular books and TV documentaries, and it was often shown as proof of a forgotten high technology. That story was irresistible. You had this tangible object from a known dig that seemed to break the normal timeline of human invention. It fit right into a bigger story a lot of people wanted to believe. A story of lost advanced civilizations or even knowledge from ancient astronauts. In those tellings, the battery wasn't a curious, debated artifact. It was a smoking gun, concrete evidence our history books were wrong. That jump from an archaeological hypothesis to a cultural myth is fascinating. It tells you less about the past and more about our own desires now. We live in a time of rapid, bewildering technological change. The idea that brilliant discoveries can be completely lost, it offers a strange comfort. It suggests progress isn't a straight line, that genius can appear and vanish, that our own era's knowledge isn't the final word. The battery became a symbol for that idea. A physical token for all the what-ifs of history. That puts a unique responsibility on the people who communicate science. Dismissing public fascination as gullibility misses the point. The stories are compelling because they tap into a real sense of wonder about human potential. The challenge is to honor that wonder, but steer it toward the more complex reality. The more interesting reality, that means presenting the evidence clearly, the successful replications, the plausible electroplating use, but also the strong counterarguments. The missing contextual evidence, the silence in the historical record. It means differentiating between a solid maybe and an unfounded definitely. A good science communicator doesn't just debunk a myth. They replace it with a richer story, a more nuanced story, one that acknowledges the mystery without needing to solve it with aliens or Atlantis. The real story is about human ingenuity in all its forms. The artisan tinkering in a workshop, the archaeologist puzzling over a find, and our own endless curiosity about where we came from. The Baghdad Battery's true power might not be in the volts it could produce. It might be in the conversations it keeps generating, bridging the gap between scholarly debate and public dreams of the past. A university physics department wanted to settle the debate. So they built dozens of replica jars, each one made to the published dimensions of the original. They used different clays, different grades of copper and iron, multiple sealing methods. This wasn't a demonstration anymore. It was a controlled experiment. The goal was to isolate every variable, to see what really mattered for the jar to function. They filled the replicas with historically plausible electrolytes, vinegar, grape juice, lemon juice, even a simple mix of water and citric acid. Then they connected them to sensitive digital multimeters. Instruments that could measure the initial voltage spike and then the slow decline over days and weeks. They tracked current output in microamps. They measured internal resistance, that inherent friction inside the cell that limits how much power you can actually draw. The results were published in a peer-reviewed journal. They gave a clear numerical portrait of what the Baghdad Battery could do. A single cell with a fresh, strong electrolyte like lemon juice could produce just under 2 volts at the moment it was activated. But that number dropped quickly. Within hours, it settled into a stable output of around 0.5 volt. The current was consistently minuscule, typically between 1 and 2 milliamps. To put that in perspective, you'd need to link over 1,000 of these jars together to produce enough current to dimly light a single modern LED. The internal resistance was very high. So the cell was excellent at creating a voltage potential, but terrible at delivering sustained power. It was, in electrical terms, a very weak source. The study confirmed the core physical principle. The artifact can absolutely function as a galvanic cell. There's no doubt about the chemistry, but the data also framed its severe limitations. This wasn't a power source for illumination or mechanical work. Its output was suited only for processes that needed a gentle, persistent electrochemical nudge over a long period. Like the slow migration of metal ions in a plating bath, the university study didn't end the argument, it refined it. By providing this rigorous baseline, it gave both sides better evidence. Proponents could point to the confirmed voltage and the ideal profile for electroplating. Skeptics could emphasize the extreme weakness and the lack of any efficient scaling method in the archaeological record. The experiment moved the conversation from could it work to would anyone have bothered. This is the gold standard of experimental archaeology. It doesn't hand you a thrilling answer. It hands you a better set of tools for understanding the question. The clay jar remains silent, but now we have a precise measurement of its whisper. A working cell needs a complete circuit. The jar could generate a tiny voltage, but to use that power, you have to connect it. You need wires, terminals. Something to carry that whisper from the jar to the object you want to affect. And the archaeological record goes silent here. No spools of ancient copper wire have been found with these jars. No clamps, no switches, no electrodes for a plating bath. That absence is the most compelling argument against it being a practical tool. It's the missing link in the whole technological chain. You think about what would have been available. An artisan wouldn't have insulated copper wire, but they had thin metal strips, beaten gold or copper foil, maybe. They had lead, which is malleable. They even had conductive liquids. A moistened linen thread, soaked in a salt or vinegar solution, could carry a small current over a short distance. These are all plausible, simple connectors. The problem is, these materials are ephemeral. A thin metal strip is valuable. After use, it would likely be melted down, reused. A damp string would rot away to nothing in a few years. If the technology was rare, confined to a single workshop, the physical evidence for its peripheral parts could have vanished completely. This forces a difficult question. If we accept the jar as a battery, are we also required to invent an entire unseen technological system around it, one that left no trace? Proponents argue the system could have been incredibly rudimentary. A single jar, a vat of gold salts, 2 metal objects, and a strip of copper to bridge them. It's a one-step process. Once the plating was done, the wire might go back into the scrap bin. In this view, the lack of surviving accessories isn't proof of absence. It's a testament to the system's simplicity and to the perishable nature of its components. Skeptics counter with a point about patterns. Ancient technologies, even rare ones, tend to leave a debris field. We find broken crucibles from metalworking, worn-out loom weights from weaving, shattered molds from glassmaking. The tools of a trade, even the humble ones, survive. If electroplating was practiced, wouldn't we find something? A unique type of ceramic vat, maybe, with residue of gold salts, or a set of copper hooks consistently found together. The total void surrounding the Baghdad Battery is deafening. It suggests that if it was a battery, it was an isolated experiment, a curiosity that never evolved into a technology with its own toolkit, because it never found a sustained, practical purpose that demanded one. This missing link doesn't destroy the battery hypothesis. It just raises the bar. It asks us to explain not just the ingenious cell, but the invisible world that must have connected it to its work. It challenges us to see innovation not in a single object, but in the delicate, often vanished web of materials and ideas that bring an invention to life. The digital age gives us a new way to look at that missing link. We can reconstruct those ancient connections now, not with clay or copper, but with code. Researchers use engineering software to build a model of the Baghdad Battery. They take the data from the physical replications, that half-volt, the high resistance, and they put it into the system. Then they run simulations. They wire multiple cells together in series, stacking the voltage. They model different loads, a tiny LED, a simple resistor standing in for a plating bath with gold salts. The software calculates everything. It shows the electron flow, the voltage drop, the total power available. And these digital experiments show something a single jar can't. They show that even if you link 10 jars for 5 volts, the internal resistance in each one is like a bottleneck. The total current stays very, very small. It confirms that lighting any kind of lamp, even a dim one, is pretty much impossible. The power isn't there, but the simulation also validates the electroplating idea. When the model connects a bank of jars to a virtual plating bath, just a specific resistance, the numbers line up. The gentle voltage holds steady. That tiny current is exactly what you'd need for a slow metal deposition over hours. The software can run this for days, compressing time, showing a gold layer forming. It can test scenarios that are too hard to build. What if they used silver wire? The difference is negligible. What if the electrolyte was weaker? It just takes longer. These models bridge millennia. They connect ancient materials to modern circuit theory. They don't prove the batteries were used this way, but they show with mathematical certainty that if an ancient artisan had connected these jars to a suitable bath, the system would have worked. It turns speculation into a viable theory. This high-tech approach pushes the hypothesis to its limit. It explores possibilities free from perishable materials. It asks the artifact through physics and computation what it was capable of, and the answer it gives is quiet, specific, and surprisingly elegant. That quiet simulation in the lab has its loudest echo in a classroom. The Baghdad Battery, it's become a lesson for students everywhere. The assignment is simple. Bring a lemon, a copper coin, a galvanized nail. Push the nail and the coin into the fruit, but don't let them touch. Connect a voltmeter to each piece of metal, and then you see the number. It's a small transformation. Ordinary fruit becomes a tiny power source. In that moment, students aren't just reading about ancient history. They're touching the same principles that might have been at work 2,000 years ago. But this project teaches more than voltage. It shows the scientific method. Students form a hypothesis. Was the ancient jar a battery? They design an experiment. They build their own model. They test variables. Does vinegar work better than lemon juice? What about an iron nail instead of zinc? They collect data. They measure the output. Then comes the crucial part. They analyze the results. They debate the conclusions. Their lemon cell produces a current, but it's incredibly weak, so they face the same question that's occupied scholars for decades. Could something this faint have had a practical use? This is where critical thinking happens. They have to weigh evidence. They learn that a successful replication doesn't confirm the original purpose. They confront the gaps in the historical record. They see that science and history aren't static lists of facts. They're living fields of inquiry, filled with mysteries that resist easy answers. The artifact's true legacy is this. It inspires active curiosity, not passive acceptance. It teaches that questioning the past is a form of respect. By building their own versions, students connect their own wonder to the long chain of human innovation. They learn that discovery often starts with a simple question about something that doesn't quite fit, and having the courage to test it themselves. That jar as a battery. You have to see it as something from an ancient economy. It wasn't just a clever idea. It was a physical object made by someone's hands, materials that cost something. The copper cylinder, that's the first clue. Copper was valuable. It had to be mined, smelted, then hammered into a thin, rolled sheet. That's skilled metalwork. Hours of labor from a specialist. The iron rod, more common but still required forging, and the asphalt seal, that wasn't just tar from the ground, it was a processed material. Gathered, heated, poured with care, each component was an investment. Time, skill, scarce resources. So you have to ask, what was the return? If the jar was for a sacred scroll, the value is clear. You're protecting knowledge, protecting ritual, something of immense cultural worth. The cost aligns with the importance, but if it was a battery, the calculation gets tricky. Its output, as we've measured, is fleeting. An electrolyte like vinegar would become depleted. The iron rod would corrode away, a sacrificial component you'd have to replace. You'd get a few weeks, maybe months, from a single cell before it needed refurbishment, before it was thrown away. For a society without mass production, that's a significant ongoing cost. Would a workshop manager allocate a skilled coppersmith's time and precious copper for a device that gives such a faint, temporary result? The romantic view sees a spark of genius. The economic view sees a ledger. It asks whether the benefit, a slightly better gold plating, a ritual tingle, whether that outweighed the tangible expense of making the thing. This perspective doesn't dismiss the possibility, it just grounds it in the gritty reality of ancient life, where every ounce of metal, every hour of daylight had a purpose. That economic reality brings us to the final way to look at the jar, the most powerful way. No one expert has the answer. It requires a conversation between fields that don't usually speak the same language. You have to imagine a lab, a different kind of lab. Around one table, an archaeologist. Her mind is full of ancient Mesopotamia, the layers of earth, the patterns of daily life. Next to her, a materials scientist. He speaks the language of electron microscopes, X-ray diffraction. Across from them, an electrical engineer. He's sketching circuits on a tablet, and then a historian of ancient technology. He knows the cultural scripts, the workshop practices that time has erased. The archaeologist starts. She doesn't see a battery. She sees an artifact's life story, where it was found, near a residential area, not a royal workshop. The chemistry of the soil around it, the fact that nothing else like it was found nearby. She provides the context, the ground truth. She asks the practical questions. Where would the vinegar have come from? Where would the used, corroded rods have been thrown away? Her work frames the object in its own world. The materials scientist listens. Then he takes the jar itself, not the original but a precise scan of its surface. He points to the corrosion on the iron. His data shows the crystal structure of the rust, the specific elements present. He can tell the difference between corrosion from slow soil acids and corrosion from an active electrochemical cell. His evidence isn't speculative. It's elemental, a physical testimony locked in the metal for centuries. The electrical engineer takes that data and the jar's dimensions. He builds a computational model. He doesn't just calculate the open circuit voltage. He models the whole system, the internal resistance of the clay vessel, the conductivity of different ancient electrolytes, the voltage drop across different possible loads, a gold plating bath, a moistened thread, a human fingertip. He translates ancient materials into modern circuit theory. He shows not just if it could work, but how it would behave under real conditions. Finally, the historian of technology synthesizes. He looks at the engineer's output, a gentle, sustained trickle of power. He cross-references it with known artifacts from the Parthian and Sasanian periods, those finely gold-plated objects, the textual records of guild secrets. Ritual practices. He asks not could they, but would they have? What cultural or economic need would this specific, subtle technology have served? He builds the bridge between function and meaning. This is the interdisciplinary model. It breaks down the walls between academic silos. No single perspective is privileged. The romantic hypothesis from the engineer has to withstand the skeptical, contextual scrutiny of the archaeologist. The archaeologist's utilitarian interpretation has to account for the materials scientist's puzzling corrosion data. Together, they aren't chasing a single, definitive answer. They're mapping a landscape of possibilities, each possibility weighted with evidence. The journey of this collaborative investigation, no matter where it ends, fundamentally changes our understanding. It teaches us that the past isn't a puzzle for one specialty to solve. It's a complex tapestry. It has to be studied from many angles. The true value of the Baghdad Battery might not be in proving or disproving its purpose. It might be in showing how we can respectfully, rigorously interrogate the mysteries our ancestors left behind. It shows that discovery isn't a moment of lone genius. It's a patient, collective conversation across time and discipline. A battery that works for an hour is a curiosity. One that works for a month could be a tool. That was the next question for the replicators. They'd proven the jar could produce a voltage. They'd measured its peak output. But for the electroplating idea to hold, the cell needed endurance. It needed to provide that gentle current long enough to actually do something. So they designed an experiment not of power but of patience. They built a new replica with care. They used the known dimensions: a clay jar sealed with asphalt, a copper cylinder, an iron rod. For the electrolyte, they chose a common 5% vinegar solution. Something any ancient household could have had. They filled the jar, sealed it, and connected it to a high-precision data logger. This device would measure the voltage not just once, but every few minutes for weeks. The jar was left in a stable room, undisturbed. The goal was to simulate a real scenario. An artisan sets up a plating bath, connects the battery, and lets it run. How long would it last before the magic faded? The initial readings were familiar, a spike to about 1.8 volts in the first hour as the reaction surged. Then the decline began. Over the first day, the voltage dropped steadily, settling around 0.6 volts. This became the cell's new normal. For the next several days, it held this level. The data line on the graph was almost flat, a quiet, dependable hum of energy. Then, after about a week, the slow fade resumed. Day by day, the voltage ticked down. 0.5 volts, then 0.4. The current, always tiny, became almost imperceptible. After 3 weeks, the output had fallen to 1/10 of a volt. The reaction was exhausting itself. The vinegar was becoming neutralized, its acid consumed. The iron rod was sacrificially corroding, its surface eaten away to produce the electrons. By the end of the month, the logger was recording voltages so low they were barely distinguishable from background noise. The battery was, for all purposes, dead. The results painted a picture of lifespan. A single charge might provide effective power for a plating process for perhaps 1 to 2 weeks. After that, the cell would need refurbishment. The spent electrolyte poured out, the corroded iron rod replaced with a fresh one, the jar cleaned and refilled. This maintenance cycle changes the story. It means the battery wasn't a permanent device. It was a consumable, a tool with a limited number of uses before it required new parts and fresh ingredients. This raises those practical questions about ancient use. Where did the worn-out rods go? Would an artisan have a basket of pre-forged iron rods ready? How would they dispose of the spent, metallic-smelling vinegar? The endurance test moves the discussion from possibility into workshop logistics. It suggests that if this was a technology, it existed within a system. A system of supply and renewal. The battery isn't just the clay jar on the shelf. It's the vinegar crock in the corner, the blacksmith down the lane, and the knowledge of how to revive the cell once its whisper had faded. This layer of realism doesn't disprove the idea. It grounds it. It asks us to see the artifact not as a static wonder, but as part of a living process. A process of making and maintaining, a process that leaves very different kinds of traces, if any traces at all. That single cell just humming quietly. It makes you ask what advanced technology really means. We usually think of scale, power, complexity, a rocket, a microchip, a whole electrical grid. Next to that, a clay jar giving half a volt seems small, like a toy, but that's our bias. Being advanced might not be about output. It might be about the leap in thinking. Seeing a connection nobody saw, an artisan noticing vinegar and copper and iron, that they interact, that they produce a steady, usable effect. That's a deep kind of knowledge. Mastery of materials, knowing their hidden properties, knowledge from watching, from trying things, not from theory. The ingenuity isn't in the power. It's in the idea that you could take a natural chemical reaction, isolate it, put it in a jar, aim it at a purpose. Whether that was plating gold or creating a sensation for a ritual, the leap is identical. It changes how we look at the past. We stop looking for ancient versions of our stuff. We start looking for the marks of a different mind, a mind that solved problems with the tools it had. With the concepts of its own time, this reframing, it's a form of respect. It says intelligence isn't a straight line, it's cultural, it blooms in different shapes. The engineer who built the Kanat, moving water through a desert with gravity, that's a genius for earth and flow. The artisan tinkering with electroplating, that's a genius for chemistry and subtle change. One isn't more advanced, they're both brilliant adaptations to their world. Our wonder about the battery, it has a hint of arrogance. We want to find our technology in their past, like that's the proof of their worth. But what if the real proof is seeing their innovations as complete, sophisticated on their own terms? That shifts everything. The question stops being, did they have our things? It becomes, what kinds of knowledge did they have that we still don't quite get? That silent jar on the shelf, it stops being a mystery. It becomes a teacher. It asks us to widen what progress means, to see that a spark of understanding, however faint, is a permanent sign, a sign of the human need to wonder. And to make. The clay jar is just sitting there in its case, but the questions around it, they're not settled. Our view of the past, it changes. It changes with the tools we have to look at it. So the future of this thing, it's not about more arguing, it's about new ways to see. There are technologies coming up. They let you examine the artifact without ever touching it. You can look inside without breaking the seal. Think about advanced 3D scanning. You could make a perfect digital copy of the jar, inside and out. The resolution would be finer than a human hair. That model, anyone could study it, anywhere, forever. It could show tool marks on the inside clay, exactly how the asphalt was put on. It could map the corrosion on the iron rod in microscopic detail. You could tell the difference between chemical patterns from storage and patterns from actual use. Then there's neutron imaging. X-rays have trouble with heavy metals. Neutrons pass right through lead or copper, but they're absorbed by lighter, organic materials. So a neutron scan of this battery, it might pick up faint residues inside. Traces of an ancient electrolyte dried to dust still clinging to the wall, or the shadow of a scroll that rotted away, its fibers leaving a mark. That one test, without damaging anything, could tip the evidence. One way or the other. Even more precise is residue analysis, mass spectrometry. You take a microscopic sample, maybe from the base where particles settled over centuries. The machine doesn't look at the material, it weighs the molecules. It could find the chemical fingerprint of vinegar, or fermented fruit, or the specific compounds that form when gold dissolves in acid. That would be a direct message from the jar's last use, a chemical whisper of what was inside it. And these tools, they change things for any new find, too. If another jar like this is discovered, maybe in a clearer place, like a metalsmith's workshop or a temple storeroom, you could use these methods right away. Analyze the soil around it for traces of metal salts. Scan for companion objects buried nearby, like thin metal strips or hooks. Context is everything in archaeology. New science lets you keep that context intact. So this mystery, it's not a closed case. It's an open invitation for future scientists to ask better questions with better tools. Each jump in technology is a new lens, a chance to see what was invisible to the people who came before. That means the story is never really finished. It keeps evolving. It can still surprise us, challenge what we think we know about innovation in the ancient world. The final chapter isn't written yet. It's waiting in a beam of neutrons, in a digital point cloud, in the quiet, lasting chemistry of the clay itself. The evidence points in two directions. Modern replication shows the jar works. It produces a small voltage with ancient materials. The corrosion on the iron rod matches an electrochemical reaction. The design with asphalt and separated metals is optimal for a galvanic cell, and the gentle output is suited for something like electroplating gold. This is empirical fact. The principle works. Then there's the archaeological context. It's a single, unique object. No others like it have been found. No wires, no terminals, no plating baths nearby. The fine gold work from that period can be explained by other techniques. No texts or artwork hint at electrical knowledge. And the simpler use as a sealed container for a sacred scroll fits known cultural practices. This side argues for the simplest explanation, fewer assumptions. The scale doesn't tip decisively, it trembles. The replications prove capability but not intent. The context suggests mundanity but can't fully dismiss the design. That's the enigma. The artifact refuses a single, clean answer. Maybe that's its purpose, a permanent question. It blurs the line between a storage jar and a scientific instrument. Between common craft and extraordinary insight, we're left with a mystery. It speaks about us too, our testing, our debates, our hopes for lost knowledge. That's part of its story now. It's become a mirror. We look at this clay jar and see our own fascination with the boundaries of ingenuity. Whether it was a battery or a vessel, its legacy is secure. A testament to the skill of its makers and to the human drive to look at a silent thing from the past and listen for the whisper of a possibility. This jar from Baghdad is still a kind of portal. It doesn't give you answers, it just challenges what you think you know about history, about ingenuity. And from the modern experiments, we know one quiet thing. The object works. You put in vinegar, iron, copper, and you get this faint, steady hum of electricity. Replication shows that it's clear, but proving it was designed for that, proving it was used that way back then, that's different. That's a much harder task. It sits in this gap between what's physically possible and what's historically likely. And that gap, that tension, that's where the value of the mystery is. It makes you ask better questions, not just about volts or electrolytes, but about how knowledge works, how a new idea gets born in a workshop, how it gets passed down or guarded or just lost. Can an insight flicker in one place and time, and then be forgotten for centuries until someone else finds the same principle again? The Baghdad Battery, whether it held scrolls or current, it makes you see history differently. Not as this steady march of progress, but as a landscape, scattered discoveries. Some take root and grow into the technologies we know, others just lie dormant. Like seeds in dry earth, waiting for the right conditions to be understood. So let this story be an invitation to look at the past with curiosity and a critical eye. To question the stories we tell ourselves about what ancient people could do, what they valued. Next time you're in a museum looking at some artifact, remember this clay jar. Think about the hands that made it. Think about the intention behind that assembly, and ask yourself not just what it was, but what it means about that human drive to explore, to find the hidden properties of the world.